How are auroras formed? This is a question that has been asked by humans since prehistoric times, thanks to the natural beauty of this light show. Nobody knew for sure what caused them, leading to speculation involving mythological elements and influencing the course of history. In 1619 AD, Galileo Galilei first used the term aurora borealis, naming it after Aurora, the Roman goddess of the morning. He thought that the lights he saw were caused due to sunlight that was reflecting from the atmosphere, but nowadays we know that that's not the case. It's true that the phenomenon happens due to the interaction of the sun with the earth, but not in the way that Galileo thought. There are a number of reasons why we can only see auroras in the extreme latitudes, near the north and south poles, and why they are only visible at certain times of the year. There are also many factors that dictate the intensity and color of the lights seen in auroras. Mainly, all of this has to do with how solar winds interact with the Earth's magnetic field. In this video, we will explore the electromagnetic phenomena that generates auroras, explaining how the charged particles of the sun interact with our planet and create this incredible light show that humanity has watched for millennia. Firstly, we must understand what solar wind is, since this is crucial for the creation of auroras. The solar wind is created by the outward expansion of plasma from the sun's corona, which is the outer part of its atmosphere. Plasma is a collection of charged particles, which are the reaction material from the fusion reactions that take place in the sun. This material is continuously heated to the point that the sun's gravity cannot hold it down, and then it's directed all across the solar system. Since the sun is so big, solar wind continuously streams from the sun's surface. However, stronger waves of solar wind may occur if the accumulation of plasma builds up more than usual.
Earth magnetic field. Earth magnetic field is a physical phenomenon comparable to a dipole magnet with poles that do not correspond with the geographical Earth poles. Earth magnetic field is originated inside the Earth and only a small part is generated on the outside and can be divided in three different fields. The first one is the core field, generated in the inner core by various systems of electric currents and is the main magnetic field generator. This field alone basically contributes to almost all the formation of the Earth magnetic field. The second one is the cross field and is generated by rock magnetized by the core field. And the third one is the atmospheric magnetic field, the only non-inner field, and it's created by the electric currents interacting with the solar wind in the atmosphere. There are four main theories about the origin of the Earth magnetic field, and these theories can be divided in magnetic theories and electric theories. The first magnetic theory states the Earth is completely magnetized, and the core and the mantle are compared to a spheric magnet oriented in the same direction of the rotational axis. The second magnetic theory states that in the center of the Earth there's a linear dipole with equivalent poles oriented in the same direction of Earth axis. The first electric theory states there is a spire at the center of the Earth with continuous current circulating into it, acting as a solenoid generating the Earth magnetic field. The second electric theory states that in the core there are two rotating plates, and when two plates rotates in a magnetic field, generates induced current, and when the current goes through a solenoid, it produces a magnetic field that is added to the previous one in a continuous process. This can only happen at a specific speed. The Lorentz force. The Lorentz force plays an important role in this phenomenon, and it's the reason of why the auroras are shaped like they are. Lorentz forces interact with the particles of the field, changing their trajectory and carving it. The particles follow the magnetic field lines with the resulting vector oriented towards the ground, and then the Lorentz force diverts the particles into an helicoidal movement. These solar wind particles interact with the other particles in the atmosphere, giving them energy and making them emitting photons. Quantum leap. The reason why auroras emit lights is because of the quantum leap, a phenomenon that can be observed when atoms absorb energy and one electron suddenly jumps to the next energy level, releasing the cumulative energy when it goes back to the previous energy level. And when this energy is released, it causes the emission of a photon. This behavior was firstly observed by Bohr during some experiments with hydrogen atoms. A photon is specified by either the wavelength indicated by the Greek vector lambda or its energy indicated by E. There is an inverse relationship between the energy of a photon and the wavelength of the light. In the case of auroras, the wavelength of the photons emitted depends on the element which electrons are doing the quantum leap, and also from atmospheric conditions like pressure and altitude.
Now that we know how solar winds are created and how Earth's magnetic field works, we can finally understand how auroras are formed. The charged particles from solar winds are emitted by the sun and directed all across the solar system. When the solar winds are approaching our planet, they face the Earth's magnetic field. Most of the particles are blocked by the magnetosphere and redirected around the planet, so that they continue to travel further into the solar system. However, some of the ions are trapped in these ring-shaped holding areas on the Earth's geomagnetic poles. These ions then collide with different gases depending on the altitude that they reach in the planet's atmosphere. That depends on the strength of the solar wind and how far down it can push the magnetic field of the Earth. The most common type of aurora color is green, and this is caused thanks to the excitation of atomic oxygen atoms found at 100 kilometers of altitude. The auroral emission lasts for 0.7 seconds, a pretty long time for a single atom to radiate away its extra stored energy. Atoms usually radiate the energy away much faster because other processes, such as chemical reactions or collisions, tend to compete in order to gain that energy. This means that if the air is denser, there will be more collisions between the atoms, causing the auroral emissions to be much shorter, which is why it's more uncommon to see other colors. At a lower altitude, usually about 90 kilometers, the most abundant gas is molecular nitrogen, which radiates in both blue and red colors, giving a purple result. This is why some green auroras can show purple at the bottom edge. On the other hand, if the air is less dense at an altitude of around 200 to 300 kilometers, the lack of collisions allows the auroral emissions to be longer, with red colors generated by atomic oxygen that last up to 100 seconds. However, since this happens at such a high altitude, the colors are difficult to see from the surface, and they can be seen more easily using cameras.
Now, other factors that affect the visibility of the auroras is that auroras are related to the environment. The sky needs to be dark and clear of any clouds. Some people claim the auroras come out when temperatures are colder, but this isn't the case. It's just that when the skies are cloudless, temperatures tend to drop. Also, there must be very little wind, so that little collision between the atoms and the movement of the auroras can be dictated by the magnetic forces. Finally, the visibility also depends on the time of the year. Auroras technically happen all the time, as Earth receives radiation from the solar winds constantly. However, we can only see their colors in specific time periods. This is more common in the equinox in March and September. During the equinoxes, the Earth's axis is tilted neither towards nor away from the Sun, resulting in a nearly equal amount of daylight and darkness at all latitudes. In the poles, this means that night will last the same, while in summer or winters it varies a lot. With this, the night sky in the poles will be dark and enough of the radiation will be visible.
It's also interesting to mention that auroras can happen in other planets. They've been seen in Jupiter and in Saturn, given that these planets also possess a magnetic field. Well, with this we can finally say that we know how auroras are formed, and it's a little bit different than how Galileo Galilei pictured it. Thank you for your attention.